Hey there. Ever tried to compare two systems that are super complex, like two weather models or two AI agents making decisions? How do you even measure how similar they are, especially when you don't fully understand their inner workings? That's the big question this research is tackling, and the answer is wild. Let's break it down. So first, let's talk about Markov chains. Those are like rulebooks for systems that change over time. Think of them as board games where your next move depends only on where you are now, not how you got there. But here's the catch. If you have two of these systems, how do you figure out how similar they really are? Traditional methods needed a full blueprint of all the rules, like knowing every possible move in the game. But what if you only have samples, like a few recorded games? That's where the magic happens. Enter bisimulation metrics. These are tools that measure how similar two systems are based on their behavior, not their hidden rules. It's like comparing two board games by watching how they play out, not by reading the rulebook. But here's the twist. Calculating these metrics used to require knowing all the transition probabilities, like every possible move. Now, researchers have cracked a new method that estimates these metrics using just samples. How? They reimagined bisimulation metrics as a type of optimal transport problem, a math concept that's all about moving things efficiently. Think of it like figuring out the cheapest way to ship goods between cities, where the cost depends on how different the city's supplies are. By framing the problem this way, they built a stochastic optimization algorithm that doesn't need the full rulebook. Instead, it uses sample trajectories, like a few recorded games, to guess the similarity. The key innovation: a linear programming formulation, solved with a stochastic primal dual method. It's like solving a puzzle where you only get partial pieces, but still figure out the whole picture. And here's the kicker. Their algorithm guarantees an epsilon-accurate estimate after a certain number of steps. Each step uses just one sample from each system, and it scales efficiently. No more guesswork. Why does this matter? Imagine training an AI to play games. If you can measure how similar different game states are, you can improve learning efficiency. Or in biology, comparing neural networks. This opens doors to better models in machine learning, finance, and beyond. Now let's pivot to another challenge: optimizing decisions in systems with multiple constraints. Ever tried balancing a scale with unequal weights? It's tricky, right? That's kind of what algorithms face when they're trying to make decisions in complex systems, like a self-driving car navigating traffic or a chef adjusting a recipe. Today, we're breaking down how these systems tackle a big challenge: optimizing decisions while juggling multiple constraints. Imagine you're designing a recipe. You want it to taste great, cost less, and be quick to make. But tweaking one ingredient might mess up the others. That's where occupancy couplings come in. Think of them as a map showing how every decision affects the final outcome. But how do you refine this map? Enter gradients. They're like directions telling the algorithm, if you tweak this variable, here's how it impacts the whole goal. It's like adjusting salt in a soup. Too much and it's ruined, too little and it's bland. But here's the catch. Algorithms can't just focus on one goal. They have to balance competing priorities, like keeping costs low and ensuring fairness. That's where dual variables step in. Picture them as invisible weights on a scale, helping the algorithm decide which constraint to prioritize. For example, if a recipe needs to be both cheap and fast, the dual variables might nudge the algorithm to cut costs first, then speed up the process. Now, how do these algorithms figure out the right balance? They use a technique called stochastic gradient ascent, a fancy way of saying they make guesses, check the results, and refine their approach. It's like learning to cook by watching a few key steps of a recipe, instead of the whole process. They sample short trajectories of data, then let the algorithm fill in the gaps. It's efficient, but it's not perfect. That's where rounding procedures come in. Think of them as a mathematical fix that tweaks the algorithm's output to fit real-world rules. If the recipe's ingredients don't add up, the rounding procedure adjusts them, maybe substituting a cheaper spice or adjusting cooking time, so the final dish works, even if it's not flawless. This step is crucial, because it bridges the gap between theory and practice. So what's the big takeaway? This research shows how complex problems, like optimizing AI systems or managing resources, can be solved with a mix of math, smart sampling, and iterative fixes. It's a glimpse into how algorithms learn to navigate uncertainty, whether they're balancing a robot's movements or predicting stock market trends. Thanks for watching. If you want to dive deeper into how these metrics work or explore the math behind optimization, check the links in the description. And don't forget to like, subscribe, and hit that bell for more explorations into the fascinating world of math and AI. See you next time.